This is the 11th topic in the course of probability and stochastic processes, in which we are going to talk about classical statistical inference. In statistical inference, we typically try to model an observation in the real life with a statistical construct, like for example, random variable or stochastic process, and so on. Now, this model usually contain a set of parameters theta, and we try to estimate these parameters that will determine later on the form of the statistical construct that we are forming to approximate these observations. And this estimator of parameters theta is usually denoted by theta hat n. Now, based on the n observations that we have, namely x1, x2, and so on until xn, then we are going to try to find the perfect model, the closest model, whose distribution, of course, depends on theta. Of course, this estimation cannot be perfect. There will be some error involved. The estimation error in this case will be theta tilde n, which is equal to theta hat n, namely the estimator that we have, minus the original or the perfect parameter theta. And the bias of the estimator is the expectation of the estimation error. So the bias, denoted by b theta hat n, is equal to the expectation of theta hat n minus theta. And this estimator theta hat n will be called unbiased if the expectation is equal to theta. So they are perfectly matched. And the estimator theta hat n is called asymptotically unbiased if the limit of the expectation of theta hat n when n approaches infinity. So that means that we need infinitely many observations to obtain that is equal to theta. This is what we call parameter estimation. There are a lot of methods that we can use to perform this parameter estimation, and one of the most widely used is the so-called maximum likelihood estimation. Now, given a set of observations, it is usually provided to us as in terms of a factor x that contains x1, x2, and so forth until xn. Each is assumed to be governed by a probability distribution with certain PDF, say fxi with parameter theta. Then the joint PDF of this set of observations, of all of them simultaneously, is given by f factor x theta, or f x1, x2, and so forth until xn theta. So this function has n parameters, of course, given that we have parameter theta. So this function has n argument, namely all of these observations. Now, the maximum likelihood estimate is a certain valuation of the parameters theta that maximizes this joint PDF, namely this theta hat n, namely our estimator. The point estimator that we have is the argument maximum theta. So we find the configuration, the valuation of the parameters theta that maximize this function, namely the joint PDF, that makes this joint PDF maximum. Now, this joint PDF is what we call the likelihood function. Now, if those observations, and usually we are able to form the observations such that they are indeed independent. If they are independent and mutually independent, then according to the probability theory, their probability can simply be multiplied with each other. Namely, the likelihood function, the joint PDF fx1, x2, and so on until xn with parameter theta will simply be given by the product of I is equal to 1 until n fxi theta. Therefore, if this is the case, if we would like to manipulate and exploit them, it is going to be easier if we take the logarithm of the expression. The logarithm of the joint PDF will simply be, we move from the product to the summation. The sum of I is equal to 1 until n, the logarithm of fxi for each one of them with parameter theta. And this is what we call the log likelihood function. Therefore, in the end, what we try to maximize instead is this log likelihood function. We try to maximize the log likelihood function such that theta hat n, namely our estimator, is given by the argument maximum theta of the logarithm of fx1, x2, and so on until xn with parameter theta. How do we maximize this? This is done by taking the first derivative of this function, of this logarithm, of this log likelihood function, and then setting it to 0. The evaluation of the parameters at that time will give us the maximum. Yeah, so it gives us a configuration that maximizes the log likelihood function. All right, let's see an example. We're going to have an example related to exponential distribution. Assume we have a Poisson arrival y0, y1, y2, and so forth until yn, where y are basically the time that something arrives, a packet and so forth. So this is a Poisson arrival. According to the probability distribution that we have before, a Poisson arrival always induces the inter-arrival time xi, which is governed by exponential distributions. So if the arrival is governed by a Poisson distribution, then the inter-arrival time, the inter-arrival is basically the inter-arrival between y0 and y1, which is, this is what we call x1, between y1 and y2, this is called x2, and so forth. This is the inter-arrival time, and the duration between the arrival. Now, each inter-arrival time xi in this case will be governed by an exponential distribution. Assume that we have n observations of these inter-arrival times, namely x1, x2, and so forth until xn. Now, we wish to estimate the rate of the underlying exponential distribution. The exponential distribution has only one particular parameter, namely the rate. So therefore, our parameter, our theta, will be equal to this rate of the exponential distribution. Now the PDF and the joint PDF, because there's only one parameter, will be given by fxi. Fxi theta will be equal to theta e to the power of minus theta xi. Therefore, the likelihood function, namely the joint PDF of all of these observations, namely the function of x1, x2, and so forth until xn, parameter state theta, will be equal to the product of I is equal to 1 until n fxi theta, which is equal to the product of I is equal to 1 until n theta e to the power of minus theta xi. Now what can we do about this? Well, we can try to find the log likelihood function, namely taking the logarithm of both sides. The logarithm of the joint PDF will be equal to, therefore, the sum of I is equal to 1 until n logarithm of theta e to the power of minus theta xi, which is therefore equal to the sum of I is equal to 1 until n, the logarithm of theta plus the logarithm of e to the power of minus theta xi. This one is simply given by minus theta xi. So therefore, this is equal to the sum of I is equal to 1 until n, the logarithm of theta minus theta xi. Now this summation here will be n logarithm of theta, while the summation here will be theta multiplied by the sum of I is equal to 1 until n xi. But remember, if we sum up all of these xi's, if we sum up all of these xi's, yeah, from x1, x2, and so on until xn, the sum is actually quite easy. The sum is exactly equal to yn because they are inter-arrival time. Yeah, so this is equal to yn. Therefore, the log likelihood function is given by n logarithm of theta minus yn theta. How do we maximize it? We maximize it by taking the first derivative, d n logarithm of theta minus yn theta d theta, which is equal to 0. And the result is n divided by theta minus yn is equal to 0. Now from this, therefore, we can solve that theta is equal to n divided by yn. This is our maximum likelihood estimate. So given these n observations, this is the best estimate that we have of the rate of the exponential distributions that govern those n inter-arrival times. All right. Now, the problem is, if we have already managed to estimate these parameters, how certain, how confident are we of this estimate? Given an estimator, for example, theta hat n of an unknown parameters theta, how confident are we of the estimator? Is it exact? Is it good? How do we measure this? Yeah, how do we know? How do we measure the confidence level of this estimation that we have? There is actually one way to do this. First, we fix a desired confidence level 1 minus alpha for some small alpha. So we decide what is alpha and we choose this one. Alpha is usually very small, for example 5%, like this one. If alpha, for example, is equal to 0.05, namely around 5%, then the confidence level will be 1 minus 0.05 is equal to 0.95, 95%. So it simply means that we have a confidence level of 95%. What does it mean? You're going to see later on. Now, once we fix the confidence level, we then replace the point estimator theta hat n, so we no longer deal with a point estimator, namely an estimator just with a particular value, by two values, namely a lower estimator theta hat n minus and an upper estimator theta hat n plus, such that, look at this, the probability that our parameter theta resides between theta hat n minus and theta hat n plus, so theta hat n minus is less or equal to theta less or equal to theta hat n plus, must be more or equal to 1 minus alpha, must be more or equal to our confidence level. This is simply similar to saying that if I do this experiment a lot, then I will find out that 90% of the time the parameters that we estimate resides in between this interval. between these lower estimator and upper estimator. Then we call this interval theta hat n minus and theta hat n plus a 1 minus alpha confidence interval. Let's see an example. Given observation, we are given n observation x1, x2, and so forth until xn, which are identically and independently, this one is identically and independently distributed by a normal distribution with a known mean but with a known variance. Assume, just for this example, we don't know the mean but we know the variance. Therefore, what we are going to estimate is just one parameter, namely theta consists of only one, namely equal to mu. Okay? Then the sample mean estimator is theta hat n. This is the point estimator. How do we find the point estimator? Just only one. This is actually easy. We just take the sample mean, namely which is equal to just these observations. We sum all of these observations divided by n, namely their average, namely 1 divided by n, summation of I is equal to 1 until n xi. So this is our estimate. Now, problem is, how do we fix the confidence level right now? Assume that we take alpha to be equal to 0.05 using the CDF phi z of the standard normal distribution. So you can find a table for this one, a standard normal distribution. We find that phi of 1.96 exactly equal to 0.05, 0.975. And this is what we fix to be 1 minus alpha divided by 2. 1 minus alpha divided by 2. Why do we divide it by 2? Because we have it left side and right side. So in this case, our alpha is 5% and our interval that we take to the standard normal distribution is at 1 minus alpha divided by 2. Then, let's continue. The probability of the absolute value of theta hat n minus theta, so the difference between the estimator and the real parameter, divided by the square root of nu divided by n. What is this? This is the variance, that, yeah, the known variance. How do we know this? Well, you can see this actually from the normal distribution, because they are identically and independently distributed by normal distribution. This is less or equal to 1.96 will be more or equal to 1 minus alpha. So how do we deal with this one? Well, we take out the denominator. So the probability of the absolute value of theta hat n minus theta will be less or equal to 1.96 multiplied by the square root of nu divided by n will be much more, will be more or equal to 1 minus alpha. And from this, then, because we have here the absolute value, we can turn this into an interval, namely theta hat n minus 1.96 multiplied by the square root of nu divided by n will be less or equal to theta, less or equal to theta hat n plus 1.96 multiplied by the square root of nu divided by n, and this will be more or equal to 1 minus alpha. Therefore, right away we find the interval that we have. This will be theta hat n minus, yeah, and this will be theta hat n plus. This is the lower bound and the upper bound of the interval. Therefore, this interval, namely theta hat n minus 1.96 multiplied by square root of nu divided by n, and theta hat n plus 1.96 multiplied by the square root of nu divided by n is a 95% confidence interval. What does it mean? It means that given the observations that we have, we are 95% confident that the real parameter, namely the mean that we are estimating, falls inside of this interval. What does it mean? It means that if we do this experiment 100 times, then 95 times of them, the parameter falls inside of this interval. This is the end of our discussion about the classical statistical inference.